Okay, this is section 6.3, trigonometric functions of any angle. Before we had looked at just trig functions of acute angles. Now we can look at any old angle. So angles, rotations, and degree measure. We're going to introduce some definitions and terminology about angles and degrees. Some of it may already be familiar to you. Hopefully it is. Definition. An angle is the result of rotating a ray about its end point. The end point is called the vertex of the angle. The position from which the rotation begins is called the initial side of the angle, and the position where the rotation ends is called the terminal side of the angle. If the rotation is counterclockwise, then the angle has a positive measure, and if rotation is negative, then the angle has a negative measure. Excuse me, that should say clockwise, not negative. So let me fix that. So if the rotation is clockwise, then you have a negative measure. This was something that was agreed to long before you and I ever came along. That counterclockwise is positive, clockwise is negative. So some examples of this. Okay, here's my angle alpha. We usually indicate how we rotate it. So you can see I rotated counterclockwise, so alpha is positive. If I started from up here and gone clockwise for beta, then that's negative. So alpha is a positive angle, beta is a negative angle. This is the initial side, that's the terminal side. And this one, that's the initial side, that's the terminal side. So alpha is positive and beta is negative. An angle is said to be in standard position if the vertex is at the origin of the Cartesian plane and its initial side corresponds to the positive x-axis. So an angle is called a quadrant 1 angle if and only if the angle is in standard position and its terminal side is in quadrant 1. Okay, now remember in the quadrants, you start in the upper right-hand corner while x and y are both positive and go counterclockwise. So it would be like quadrant 1, quadrant 2, quadrant 3, quadrant 4. So similarly for the other three quadrants. You have a quadrant 1 angle, quadrant 2, quadrant 3 angle, quadrant 4, and so on. An angle is called a quadrantal angle if and only if the angle is in standard position and its terminal side lies on a coordinate axis. So here alpha, I rotated that way. This is the initial side. The red ray is the terminal side. It's a quadrant 1 angle. Beta started here at the x-axis. I rotated clockwise, and its terminal side is in quadrant 4, so it's a quadrant 4 angle. Now, again, we number the quadrants with uppercase Roman numerals. So again, this is quadrant 1, where x and y are both positive, and then go counterclockwise. So quadrant 1, quadrant 2, quadrant 3, quadrant 4. And then here theta. I started at the x-axis, rotated clockwise, and stopped on the negative y-axis. It's a quadrantal angle. And notice if you can measure stuff, that's a right angle, that's a right angle, that's a right angle. So this theta is actually 270 degrees. It went through 3 right angles. Okay. Two angles are called coterminal if only if they have the same initial sides and the same terminal sides. Now, it sounds like they're the same angle, but not necessarily. So here alpha went positive, beta went negative. They're coterminal. An angle is said to have a measure of 1 degree, denoted like this, 1 with the little degree symbol here, the little open circle, if and only if the angle subtends 1/360th of a complete rotation. So in case you're wondering why are there 360 degrees in a full circle, full rotation, that's why. The real question is why they pick 360. If you think back about how many days are in a year. So notice that this means that a complete rotation equals 1 full circle, which is equal to 360 degrees. We can use this fact to find coterminal angles. So again, one full rotation is 360 degrees. So we just add and subtract 360 degrees to the given angle. That's all you do. That's how you get coterminal angles. So for each given angle, we're going to find two positive coterminal angles, and then in part B, two negative coterminal angles. We're going to simplify our answers. In other words, do the math. That's what simplify is going to do. So here's our first one, 58 degrees. Okay, for part A, we're going to add 360 degrees twice. So, because remember, we wanted two positives. So 58 degrees plus 360 degrees, we get 418 degrees. That's coterminal. Notice you had to go around once and then stop at 58 degrees. And now add another 360. So 418 plus 360, I get 778 degrees. Very hot angle. Now to get the two negative ones, we'll subtract 360 twice. So subtract 360 twice to get the two negatives. So 58 degrees minus 360 degrees, negative 302 degrees. Then subtract 360 again, negative 662 degrees. Those are my two negative coterminal angles. Notice there are a bunch of coterminal angles to any given angle. Just keep adding, subtracting 360. Number 2, I have negative 577 degrees. Notice the fact this is more than negative 360 says this angle already went around more than once. So let's see, if we add 360 degrees, we get negative 577 plus 360, we get negative 217. It's still negative. So notice this could be an answer for part B. So to get something positive, I got to add another 360. So I'm going to have negative 217 plus 360. I get 143 degrees. That's one positive coterminal angle. Add 360 degrees to that, you get 503 degrees. So there are my two positive coterminal angles. Notice the answers are not unique. I'm basically finding the first ones. Now for part B, negative 217 is already one answer. Now to get another one, I can subtract 360 from the original negative 577. Now if you subtract it from the negative 217, you're back to negative 577. So negative 577 minus 360 degrees, I get negative 937 degrees. So there are two negative coterminal angles. Okay, trig functions of angles or rotations. The negative angles and angles greater than 360 degrees allow for rotations in either the clockwise or counterclockwise directions, and for rotations that go around a full circle several times. That could be kind of aggravating, but if you think about the spoke of a bicycle wheel, it's generating an angle, and if all you could do is 360 degrees, you'd only rotate around once. It wouldn't go very far. So the classic example of the situation again is a wheel. A spoke or particular radius of the wheel is rotating through larger and larger angles, either the positive direction or negative direction, as the wheel goes round and round. Keep that in mind. Okay? That wheels generate angles. We want to look at the trig functions of those rotations, or what is equivalent, the angles made by those rotations. So, reference triangles. Consider a triangle with one vertex at the origin of a Cartesian coordinate system, another vertex somewhere on the positive x-axis, and the third vertex at a point P that is located on a circle of radius r and center at the origin. Okay, let's kind of draw a picture of that. Okay, so recall from section 1.1, again that's in the algebra portion of our pre-calculus, that the equation of a circle with center at the origin and radius r is x squared plus y squared equals r squared. Okay, so that's the equation of a circle, center at the origin, radius r, x squared plus y squared equals r squared. So we have a picture of the situation on the next slide. Remember, one vertex at the coordinate, at the origin of the coordinate system, another vertex somewhere on the positive x-axis, and the third vertex is at a point P on a radius of length r. So O for origin. Here's my point P. Here's one side of the triangle. Here's the other side. This point Q is also on the origin. So there's a picture of what we're talking about. Now P has coordinates x, y. Remember, this circle has radius r, so that length is r. From O to P is r. So again, this is the same picture, only smaller. So notice that the angle at the vertex is in standard position. namely that angle right there, the angle QOP. The triangle POQ is called the reference triangle for the angle at the origin, this angle O. Okay. So this is the reference triangle for that angle. So reference triangle. We then have the following for angle O. Now again, remember, this length is x. From O to Q is x. From Q to P is y. And from O to P is r. OPP is equal to the y-coordinate of P. Again, thinking about opposite. ADJ is the x-coordinate of P. And then OP is r. That would be HYP. Now, if you think about how we defined the trig functions for right triangles. So we want to be consistent. So these, y is OPP, x is ADJ, and r is HYP. So let P with coordinates x, y be any point other than the vertex on the terminal side of any angle theta in standard position. Let r equal the radius of the circle with center at the origin that passes through the point P. So basically the picture we have. Notice that the equation of the circle is x squared plus y squared equals r squared. Keep that in mind. We then have the following 6 trigonometric functions of theta. Sine of theta is equal to y over r. Cosine of theta will be x over r. Tangent of theta is y over x. Okay, this is still like opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. Remember, these 3 over here on the right, we'll flip those 3 over. So, cosecant of theta is r over y. Secant of theta is r over x. And cotangent of theta is x over y. Okay, please don't confuse those two because they just look so similar. So there are the 6 trig functions of theta when it's in standard position. Triangle with vertices at the origin, P, and the third vertex lying on the x-axis is called the reference triangle for the angle theta. Notice this definition, it is now possible for some of the trig functions to be positive, negative, or even undefined. Going back here, they have these denominators. Now, r is a radius of a circle. It can't be 0. But notice, x and y could be 0. Right? X and y could be 0. So deciding the sign, the algebra sign of a trig function of theta comes down to determining where the terminal side of theta lies and knowing the signs, again, the algebra signs of x and y in each quadrant. Now, some people make you memorize, but I think it's easier just to look at the pictures. So it's also important that you know the degree measures of the coordinate axes. Okay, so again, this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. Okay, the x-axis, when you start, is 0 degrees. When you hit the positive y-axis, 90 degrees. The negative x-axis, 180 degrees. Then the negative y-axis, that's 320. I don't have, not 270. I don't have a label, but that should be 270. 180 degrees plus 90 degrees. And then when you end up back to the positive x-axis, you're back at 360. Again, these are the algebra signs of x and y in each of the quadrants. In quadrant 1, they're both positive. Notice if you think about the picture, you're on quadrant 2, you're to the left of the y-axis, but above the x-axis. So x is negative, y is positive. In quadrant 3, you're to the left of the y-axis, to the left of the y-axis, below the x-axis, so both of them are negative. Again, remember, the x-coordinate measures how far to the left or right you are from the y-axis, and the y-coordinate measures how far up or down you are from the x-axis. Some examples. So given that theta is an angle in standard position, determine in what quadrant theta lies. Again, pictures will help. So the sine of theta is less than 0 and the cosine of theta is greater than 0. Remember, sine goes with y, cosine goes with x. Remember, r, since it's the radius of a circle, is always positive. So sine of theta less than 0 means y is less than 0. So far we know we're down here below the x-axis. So this is my shape. Okay, then cosine of theta greater than 0, that says x is positive. So that would be the right side. And where do they overlap? Quadrant 4. So theta is a quadrant 4 angle. Number 2, tangent of theta is greater than 0 and the cosecant of theta is less than 0. Now, tangent is y over x, so it takes both of them. Positive over positive is positive, but a negative over a negative is also positive. Now, cosecant of theta. Remember, cosecant is the reciprocal of the cosine. So the cosine uses x, so cosecant will use x. So we're going to analyze the tangent last because it takes both of them. Now, cosecant less than 0 means that y is less than 0. I may have said that wrong. Cosecant is reciprocal of sine. So, y less than 0, we're below the x-axis. Okay, now, going back to the tangent. Since y is less than 0, and the tangent is supposed to be positive, that means x also has to be negative. So a negative over a negative is positive. So x being negative says we're to the left of the y-axis. So where do they overlap? Quadrant 3. So we have a quadrant 3 angle. Okay, number 3. The tangent of theta is less than 0, but the cosecant of theta is greater than 0. Now the secant is the reciprocal of the cosine. The tangent needs both x and y, so we'll do it last. So secant of theta uses x. So x is greater than 0. So the right of the y-axis. Now, tangent less than 0. So that means x and y have opposite signs. We've already established that x is positive, so y must be negative. So y is negative below the x-axis. They overlap. Quadrant 4. Got a quadrant 4 angle. Now, if you don't get overlapping in one quadrant, it could be overlapping in 2 quadrants, in which case you've narrowed it down to 2 quadrants. Okay, number 4. Theta is equal to 167 degrees and 22 minutes. Okay, remember 0 degrees, 90 degrees, 180, 270. And if you get it back up here, you're at 360. So 167 degrees, 22 minutes, it's between 90 degrees and 180 degrees. So our theta is a quadrant 2 angle. Number 5, theta is equal to 930 degrees. Pretty warm angle. Okay, now notice it's bigger than 360, so you went around more than once. Okay, to find out how many revolutions, we divide theta by 360. So 930 degrees divided by 360 degrees, I get 2.583333. So I did go around at least twice. Notice a little bit more than 2.5. So we've gone around 12 times, and we still have some fractional part of the revolution left to go. We have to figure out how many degrees are in this fractional part. So we're going to multiply this 583333 forever by 360. Remember, there are 360 degrees in one revolution. So again, I did it in the calculator so you can see what did I actually do here. You understand what I'm saying? So I did 930 divided by 360. Enter. Okay, subtract off the 2. Because remember, this is a repeating decimal, and I can't, literally type 333 forever. Then times 360. 210 degrees. So I made 2 complete revolutions with another 210 degrees left to go. So now 210 degrees is bigger than 180. So 180 plus another 30, right? So I'm in quadrant 3. Okay, number 6. Theta is negative 1,000 degrees. So notice I went clockwise. I got to figure out how many times did I go. So we're going to determine that by dividing by negative 360. So let's see. Now it's just kind of a weird coincidence. 0.7777 forever is 7/9, if you really want to know. But 5. Clear that off. So negative 1,000 divided by negative 360. Subtract off the 2 times 360. Turn 80 degrees. Remember, technically all of this was negative, so. I get negative 280 degrees. So in our picture, negative 90, negative 180, negative 270, and just a smidge more to get negative 280. So I'm in quadrant 1. So I've got a quadrant 1 angle. Okay, some more examples. Find the exact values of the 6 trig functions of theta if theta satisfies the stated conditions. Simplify, do not rationalize denominators, do not use mixed numbers of estimates. Again, rationalizing denominators is, to me, just a complete waste of time. It's one of those things done to annoy algebra students. So theta is an angle in standard position, and the point negative 47 is on the terminal side of theta. I've got my x, I've got my y. So I got to use x squared plus y squared equals r squared in order to find r. So negative 4 squared plus 7 squared is going to be r squared. So 16 plus 49 is r squared. 65 is r squared, so r would be the square root of 65. Okay, now remember, since r is a radius, don't do the plus or minus. It's always the plus one. And square root of 65 is simplified. So sine of theta, remember, is y over r, so 7 over square root of 65. Cosine is x over r, so negative 4 over square root of 65. Tangent of theta is y over x. So 7 over negative 4, if you like, negative 7/4. It doesn't matter where you put the minus sign, but put it somewhere. These 3, flip those 3 over. So cosecant of theta is square root of 65 over 7. Secant of theta is square root of 65 over negative 4. And the cotangent of theta is negative 4/7. Again, the things that are negative, you don't really have to put them with their x or the y, but put them someplace. Some people like to put them with their x or y. Some people like to put them in front of the fraction. As long as you put it somewhere. Okay, theta is a quadrant 3 angle, and the tangent of theta is equal to 4. Remember, technically 4 is 4 over 1 for a y over x. So in quadrant 3, both x and y are negative. So the tangent of theta being 4 is equal to y over x. Now remember, x and y are both negative. So I can think of it as negative 4 over negative 1. So I've got my y, I've got my x, got to get my r. So r is going to be the square root of x squared plus y squared. Square root of negative 1 squared plus negative 4 squared. So I get square root of 1 plus 16, square root of 17. I now have everything I need. Got my x, got the y, got the r. So the sine of theta is going to be, remember, it's y over r, so negative 4 over square root of 17. Cosine of theta is going to be x over r, so negative 1 over square root of 17. Tangent of theta is given, 4. Again, don't write it as negative 4 over negative 1. That would be simplified. Cosecant of theta is the square root of 17 over negative 4. Secant of theta is the negative square root of 17. And lastly, the cotangent of theta is 1/4. Okay, number 3. Theta is a quadrant 2 angle whose terminal side is parallel to the line y equals negative 4/7x minus 19. Okay, the terminal side of theta is on the line y equals negative 4/7x. Okay, how do we know this? Okay, remember, parallel lines have the same slope. This guy has slope negative 4/7, so we have slope negative 4/7. Now, how do we know that the y-intercept is supposed to be 0? Remember, the terminal side goes through the origin. The y-coordinate of the origin is 0. So the terminal side of theta, the slope, the line always looks like y equals mx. Okay, so I've got y is equal to negative 4/7 x. And so here's our explanation of why the y-intercept is 0. Okay, we must now choose an x value that is in quadrant 2. We look at in quadrant 2. So x values in quadrant 2 are negative. Now, you're free to pick anything you want that's negative, but I want to pick something easy that'll make this fraction go away. So the easy thing in quadrant 2 for x, quadrant 2 x is negative, the easy thing to me is negative 7. So if I plug in negative 7 there, I'm going to get y is equal to negative 4/7 times negative 7. So my 7's cancel, right? And minus times minus is plus, so I get 4. So x is negative 7, y is 4. Got to get my r. R is going to be the square root of x squared plus y squared. Square root of negative 7 squared plus 4 squared. Square root of 49 plus 16. Square root of 65 again. Ooh, I like that. Okay, so my x is negative 7, my y is 4, my r is square root of 65. So the sine of theta is going to be y over r. So it's 4 square root of 65. Cosine of theta is going to be x over r. So negative 7 over square root of 65. The tangent of theta is y over x. So negative 4/7. Then the cosecant, square root of 65 over 4. Secant, square root of 65 over negative 7. And lastly, the cotangent is going to be negative 7 times. Reference angles. Remember we had reference triangle, now reference angles. We like to deal with acute angles because that lets us use right triangles. Remember, acute angles are between 0 degrees and 90 degrees. In terms of angles in standard position, this would put us in quadrant 1, where both x and y are constant. To set up the definitions for the trig function of the angle, or the trig functions of rotations, we had the idea of the reference triangle. All we really need is the acute angle whose vertex is at the origin. So this leads to definition. Let theta be an angle in standard position. The reference angle for theta is the acute angle between the terminal side of theta and the x-axis. Always measure to the x-axis, even if the y-axis is closer. So the angle between the x-axis, or I guess I should say the closest side of the x-axis, and the terminal side of theta. So notice since it's an angle between, it's always going to be positive. Some notes on this. Reference angles are always acute angles. Always, 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 always. Reference angles are always measured between the terminal side of theta and the x-axis. Never measure to the y-axis for reference angles. Number 3, the trig functions of reference angles are always positive. Because they're acute. What is the big deal about reference angles? Other than they're nice, simple angles. A circle that's centered at the origin enjoys symmetry with respect to the origin, x-axis, and y-axis. It's a circle, it has all kinds of symmetries. This leads to the following. Fact. Let theta be any angle, and let t be the reference angle for theta. Then if trig represents any of the 6 trig functions, we have this. The absolute value of the trig of theta is equal to the trig of t. If you're wanting the exact values of the trig of theta, we have to figure out in what quadrant does the original theta lie in. In order to get the signs correct, the algebra signs, for the trig functions of the original theta, we must look at the quadrant in which theta lies. Some examples. Find the reference angle for each given angle theta. Theta is 285 degrees. So since 285 is less than 360, it has not made a complete rotation, we sketch the angle in standard position. Okay, so notice 285 is somewhere in here. So that's my 285 degrees. This is the reference angle. So we're going to take, remember we're supposed to go to the x-axis, the closest part of the x-axis. So the reference angle would be 360 minus 285. So the reference angle is 75 degrees. It's the angle between them. Number 2, theta is negative 300 degrees. So again, we draw the angle of standard position. Now, it's less than negative 360, so we didn't go around more than once. So let's see, negative 90, negative 180, negative 270. So somewhere in here is negative 300. Okay, this is the reference angle. Okay, now with negative numbers, you got to kind of think backwards. Remember, negative 300 is bigger than negative 360. It's not as negative. So the reference angle would be negative 300 minus negative 360. Okay, if you subtracted backwards, like if you did negative 360 minus negative 300, notice you would have gotten negative 60. Since we know we're supposed to have an acute angle, that just says you subtracted backwards. Get rid of the minus sign. But the picture does have. Ooh, theta is 2200 degrees. Okay, so we definitely went around more than once. So let's find the number of rotation. We're going to do 2200 divided by 360. So we went around 6.1111 times. So if you lop off the 6 and multiply by 360, you're going to find the number of degrees in that fractional part of rotation. So I got 40 degrees. How nice. It's already acute. That is the reference angle. If the angle had not been acute, we would need to do what we did in example 1. Theta is 3800 degrees. So do 3800 divided by 360. I get 10.55555 forever. So subtract off the 10 and multiply by 360, and you get 200 degrees. So you went around 10 times, and then you had to go 200 more. So 0, 90, 180, okay, 200 is somewhere in there. This angle right here, that's the acute angle. So that's the reference angle. So again, it's going to be 200 minus 180, 20 degrees. I don't know why I changed that to 5,000. It is 380. Quick and dirty way to find reference angles. It is quick and it is dirty. The method for positive angles. Find the number of rotations when you divide by 360. Find the leftover angle. Subtract rotations from step 1 and multiply the resulting decimal by 360. You should now have an angle that can be drawn in standard position. If the angle is in quadrant 1, that is the reference angle. If the angle is in quadrant 2, it's 180 minus the leftover. Quadrant 3, it's the reference going to be the leftover minus 180. And for quadrant 4, the reference is going to be 360 minus the leftover. Again, I think it's better to draw pictures. The method for negative angles. You've got to kind of think backwards on this. Find the number of rotations, we're going to divide by negative 360. Find the leftover angle, so subtract rotations from step 1 and multiply the resulting decimal by negative 360. You should now have an angle that can be drawn in standard position. Again, if it's in quadrant 1, it's going to be the leftover minus negative 360. If it's in quadrant 2, the reference will be negative 180 minus the leftover. If it's in quadrant 3, it's going to be the leftover minus negative 180.